energy in your engine. They're how they activate the explosion of the fuel mixed with oxygen. That then causes the cylinder to expand, and that pushes the arms, or actually there's several engine designs after that, but usually it's arms. Now, so biological catalysts. These are biological catalysts. They're enzymes. You've all probably heard of enzymes before. So everybody has heard of an enzyme, and you've experienced an enzyme. Your saliva is an enzyme. And so you've all experienced catalysts before. You've been taking advantage of them continuously all the time. When you breathe, included.
Okay. I hate building models. It is not that I don't know what we're talking about. It's for the life of me. I cannot put it on.
Spend some time with me. I'll show you some tricks.
Computer program.
Okay. So biochemical reactions are going to use enzymes to increase your reaction rate and make the reaction faster. Okay. Most enzymes are going to be proteins, but they don't all have to be proteins. In fact, there's RNA ones. There's a few other parts of them that are not proteins or RNA. And so not every enzyme is a protein, but the majority of it is. Okay. The enzymes that enhance a chemical reaction, they can enhance it by a factor of 10 million. For example, one of the fastest enzymes is the enzyme that converts CO2 to carbamic acid in your blood. And then when you breathe out CO2, it converts it back. Okay? So did anybody think you transport CO2 in your blood as CO2 or as on like hemoglobin? So some biology books actually say you transport CO2 on hemoglobin. And they're like middle school biology ones, and they're really, really bad books. Yeah. But you do not. You transport it as an acid, which is carbamic acid, and then it gets converted back at your lungs so you can exhale the CO2. Okay. The enzymes that increase the speed of reactions are going to do so usually by immobilizing these substrates, is what they're called, but you recognize them as reactants. So the reactants that have to bind to the enzyme, they bind, and then they are oriented the correct direction, very near to each other. So they basically just hit each other in the correct orientation a bunch of times. Okay? And if you can orient everything the correct orientation and they end up hitting each other more often, you speed up reactions, don't you? And so that's how most enzymes work. Okay? It's also why you actually would call the reactants are actually called substrates when you're talking about enzymes, because they actually have to bind to the enzyme first. Okay? This right here is what's called the lock and key model. It's sort of the entry-level, most basic model of how enzymes work, and it's a pretty easy one to understand. So what you have here is you have the enzyme. It has an active site. It's going to be shaped similar to those reactants so that it can bind nicely to those reactants and have them in the proper orientation. Okay? The reactants will then bind into that substrate, that enzyme active site, and that's going to orient them correctly so they continuously are hitting each other in the correct orientation. Okay? They'll be really close to each other. And that's going to prompt a reaction. Once it reacts, they'll release from the enzyme, and then you can take new ones in. And remember, the enzyme is a catalyst, so it's speeding the reaction up, but it does not get consumed in the reaction. Okay? Okay. Anybody have any questions about that so far? Okay. There's another model, by the way, that's a better model, more accurate. It's called induced fit. And it's more thinking about like when you go in for a handshake, you don't just keep your hand the same shape, right? You fit it. And so when these bind, they actually cause the enzyme to change. Okay? It's not that much more complicated, but we don't have time to go through all the different models. So that's a good enough model for you to understand enzyme activities. Okay? Now, enzymes are going to be highly specific to the reactions that they catalyze in their body. The exact shape of that active site, the shape of those enzymes, actually dictates the function. Okay? So think of it a bit like this. If you go into a factory and you see like a press, all presses look alike, don't they? They bring them down, they press on, they usually clench around, right? And so press, in a factory, right? And you usually have a little line that moves things through, right? Or some sort of rotor. And so if you ever see one of those, you've kind of seen them all. They all look similar, don't they? If you ever were to look at the ATPase, which is the enzyme that finishes making ATP, it actually looks like that. So far as it literally has a crankshaft.
Mm-hmm.
Okay. Yeah, it looks exactly like a. Have you ever seen the Coca-Cola presses that put the caps on?
Mm-mm.
Okay, so if you ever see one of those, it literally takes like a deal, clips it in, moves it over, and then it has a press that comes down and goes thunk, and then it brings around and releases. And that is exactly how ATPase works. And ATP is made. So they look exactly alike. Okay. And it's because form is function, right? The form of a tool dictates its function. The form of an enzyme dictates its function. Okay, so when they're defective, the result is often going to be a disease state in the organism. Though keep in mind, just because you have a defective enzyme, if you basically never use that enzyme, you won't know, will you? And so this is why, for example, dietary changes oftentimes spark off diseases in people that they never knew they had. Okay? And why they sit like you'll eat and eat and eat, and you'll have weight issues for like 20 years, and then all of a sudden, bam, it gets you. Because you start having those defective enzymes really actually matter in 20 years. Yeah. So one of the examples of this is, for example, albinism. Yeah. That's the lack of pigment in the skin, hair, eyes. It's caused by a defect in tyrosinase. This is actually the enzyme in the pathway that produces the pigment of melanin. Notice there's only one enzyme in that pathway. And so that actually causes you to not produce the pigment. And because you don't produce the pigment, you don't have any coloration. Okay? Which is albino. Okay. These are some different examples of these, by the way. Note that these do not have to be defective in as they don't work at all. They can just be defective as in they do not work as well as they should. Okay? All of us probably have some form of genetic disease where we have enzymes that do not work as effectively as they could. Okay? If I was to estimate the number of individuals on the planet, the percent of individuals that have fully functioning everything, it's probably in like the 1%, if even that. Okay? But usually the amount of defectiveness is not sufficient to actually make any problems. Okay? Now, the synthesis reactions, these are going to occur when smaller molecules or atoms combine to create larger molecules. Synthesis reactions often require energy because products have higher free energy, i.e. less random, than reactants, which are more random. Because you have more reactants, you take that down to less reactants. And so, by definition, you're decreasing the entropy in these. Decomposition reactions is going to break apart larger molecules to form smaller molecules. Now, whenever you do this, what you're going to notice is that because we're breaking them apart to form smaller molecules, more often than not, we're going to release energy. And so these tend to be your like your metabolism reactions where you create energy. Okay, they'd be decomposition reactions. Exchange reactions, sometimes they're called displacement reactions. These are going to involve both of these processes. Okay, and so we'll have a synthesis and decomposition. We break something apart and we make something else. We don't have it becoming more complex or less complex. We usually have the same reactants, same number of products. Okay, so this is actually an example of these reactions. So here we have amino acids being assembled into a protein, and that's going to be a synthesis, right? We're making that protein, synthesizing it from the parts. Okay? And so, amino acids, protein synthesis. If we have, say, let's say we eat some starch, right? We have some potatoes this morning. and we start breaking those potatoes down, that's going to give us glucose, isn't it? Okay? And so that right there is actually going to be a decomposition reaction. Okay? We're breaking apart the starch to get the glucose. All right. Now, this one right here is an exchange reaction. See how we don't actually get like more complex or less complex? We don't have a change in the number of reactants per se. What we're getting is we're getting an exchange. We're exchanging the magnesium and chloride together, and then we have the H and the OH coming together to give us water. Okay? And so that would be an exchange reaction. Now, there are single and double exchange reactions. So again, this would be synthesis. Two things come together to give you the third thing, the product. Decomposition, we have a larger thing breaking apart two smaller things. And exchange, we don't have any real difference here. We just exchange one from the other. So if we have a single exchange, we're going to exchange one item between the two. Okay? So one of those groups, one of those atoms is going to exchange. Over here, we'd have a double exchange. Notice we exchange both. Okay. All right, so let's talk a bit about reversible and irreversible reactions. So reversible reactions can form products in either direction. And so we can go back and forth in these reactions, assuming we provide the energy to do so. Okay. Now, if the chemical bond can be formed with enough input of energy, it can also be broken, so you can go back and forth. The reversible chemical reactions will be indicated with a pair of arrows. Apparently, something has changed with Microsoft Office, and all my double arrows is no longer a character they can do. So I don't know what to say about that. But anyways, it looks, I'm going to write it in real quick, like this. Okay? That's what that should have looked like. I don't know why they keep breaking the characters. There must be like patents or something on these things. Anyways, that double arrow means this can go back and forth, right? And so that's a reversible reaction. Okay? Most of the reactions you've seen and actually talked about before have been the single arrows. The single arrows means it's an irreversible reaction. It cannot go back and forth. Okay? At least under normal conditions. Now, the forward reaction is going to occur when we have A plus B, and that gives us AB. And so that would be the forward reaction. The reverse is actually going to be where these break apart and reform that A plus B. Okay? You'll notice they're actually pretty common in our body. And so, for example, we produce glycogen, which is how we store sugars. Then we break that apart. We produce glucose so that we can feed our brains. And then we break that glucose apart to get energy back out of it. And so this is actually pretty common, though the actual reaction pathways typically do not have all equilibrium arrows. Okay? All reversible reaction arrows. So at the point when both the forward and reverse reaction are occurring at the same rate, the reaction is going to be said to be in a state of chemical equilibrium. And what chemical equilibrium means is that the forward reaction is going the exact same speed as the reverse. So we don't see any overall change. Okay? Think of it a bit like a park. A park has a certain number of people that can be in it, right? When we're talking about like Disneyland. And so they have gates where they measure the number of people that come in and the number of people that come out, right? And then what they do is they keep those numbers the same. And so a park being full, like Disneyland, is a chemical equilibrium, right? Okay. Now again, it's the rate of these reactions that is equal. It is not the amounts. Okay? The amount of A here does not have to be the same as AB by any means. Okay? You can have a chemical equilibrium where the majority, the vast majority, is on one side. And then the very tiny amount is on the other. Okay? These could be like 10 to the 20 versus 10 to the negative 20. Right? The only thing that's equal in equilibrium is the overall exchange. How fast the reactions are going in each way. So you'll have no overall change.
Products and reactants can be at various levels.
Exactly.
But how fast the exchange is happening is the equilibrium.
Exactly. And so you will see no overall change in it. And this is called dynamic equilibrium, by the way, because you will have continuous exchange between the two. Now, reactions that are highly exothermic for practical purposes will be considered irreversible reactions. Basically, what that means is that you're not going to be able to get enough energy in normal conditions to go backwards. Okay? The easiest way of thinking of the irreversible versus reversible reactions is think of them like the staircase. Okay? When you go up a stair and you fall back down off the stair, can you go back up? Yeah, you can go back up. And so it's not a problem, right? Reversible reaction. We can go back and forth pretty easily. Okay? Maybe you can do that with 2 stairs, right? Okay, if your legs are long enough. What happens, though, if we go from the 2nd floor and we fall backwards on the staircase? Yeah, are we going to be able to jump right back up to the 2nd floor? No. So that's going to be an irreversible reaction, right? Same thing here. If you were to jump out the window here, you're not going to be able to jump back up, are you? No. And so that would be an irreversible process, right? Or an irreversible reaction. Okay? Now, interestingly enough, like you could jump out the window here and not actually get injured. Like I actually jumped off a 3rd floor once and I did not get injured. That was when I was lighter. I'm pretty sure I'd get injured now if I jumped off the 2nd floor. I'm a bit heavier now. Actually, I fell backwards off of a 3rd floor once. Yeah. And I actually twisted around and then landed almost on my feet. Yeah. I've fallen 20 feet off of a cliffside into a shale pit, too. That one hurt. But that one caused rocks to be embedded in my bone.
Yeah.
And it's like hairline fracture, but I'm okay. Uh-huh. Yeah. It hurt, but not that bad. It's like it's not even in the top 20 most painful things that have happened. The scorpion poison hurt more. The electrocutions hurt more. The flying off my bike at 40 miles per hour hurt more. Okay, so combustion. Yeah, I've almost died a lot of times, by the way, in case you're wondering. Okay, combustion. This is going to involve organic molecules reacting with oxygen to produce carbon dioxide and water. And so this is exactly what you think it is. Everybody knows combustion pretty well, actually. Our society is essentially built on it right now. So, combustion reactions are going to tend to be very highly exothermic. Typically are considered irreversible. Like if you were to try to reverse your engine burning the fuel, that's not going to happen, is it? No. So typically going to be considered irreversible. So combustion reactions are going to be a type of decomposition reaction. They're also going to be what's called an oxidation reduction reaction. Okay? Now remember that oxidation reduction are going to be reactions that it's always paired. You always have an oxidation, you have a reduction. You have a reduction, you have an oxidation. Okay? Okay, and I'll oftentimes call them redox reactions. Now, combustion reactions, please don't make me speak over you. Combustion reactions are going to use oxygen and produce energy, whether it dissipates as heat or performs work. The reaction is going to be important parts of understanding any fuels, because that's the majority of fuels are going to be redox reactions that are combustion reactions. Okay? The molecules are always going to be carbon dioxide. Whenever you produce these, you actually burn completely. You should get carbon dioxide and water. Okay? Which is, if you look at a properly functioning car with a properly functioning catalytic converter, is all that comes out. Okay? And you look at the tailpipe and maybe you see some like steam coming out. That's the water. You don't see the carbon dioxide at all. Okay?
Is that what the catalytic converters are for?
It is. Yeah. So I don't know if you guys know this, but other than CO2 being considered a pollutant, about 90% of the pollution on the road is actually produced by about 10% of the vehicles. Yeah. And that's because if you have a functioning catalytic converter and it's working properly, it's going to convert all the NOx, the nitrogen oxides, back into just nitrogen gas, which is our atmosphere. And it will complete the burning of all the carbon monoxide to carbon dioxide. And it will also complete the combustion of all the what are called black fuel bodies. Because if you do not completely burn stuff, you get something called soot, right? Yeah. Which is unburned carbon bodies. Okay? And so that'll complete those combustions as well. Yeah. They do actually decay over time, but they are a catalyst in there. Mm-hmm. So they can be reused over and over. Mm-hmm. If you clean them, you can keep reusing them again. Mm-hmm. Yeah. The catalyst is quite expensive, so people steal them a lot. Right. Yeah. But, yeah. A funny little fact, has everybody ever seen, like in the movies, people try to off themselves by like sitting in a garage with their car? If you have a functioning catalytic converter, that will take like 12 hours. You still won't actually die. To actually kill yourself, you would have to have a complete air seal of the room, and you'd suffocate to death because of the CO2. Now, people used to be able to do that back before you had good functioning catalytic converters, because you'd produce carbon monoxide, which would blind to your hemoglobin and cause you to suffocate. But a new car cannot do that. And the funniest one is when people try it with electric vehicles. Which is even more funny because the electric vehicles are actually more dangerous. Like, you could very easily light yourself on fire in electric vehicles. Yet, I don't know what to think there. It's actually not very funny if you start thinking more about it, but it is. Wow. All right, so again, understanding fuels, a very important part of the world. Whenever you see clean burning cars with properly functioning catalytic converters, and you see people like looking at those white smoke clouds coming out of them, those are water. The only reason you can see them is because it's usually cold out, and so it's converting to the crystals, ice. Okay, so alkanes. Alkanes are generally considered unreactive. They do undergo combustion, however, and so you can combust them. Alkanes are going to be excellent fuel sources because they have a very high energy density. That means they give off a lot of energy when you burn them. Okay? And burning things is really easy to do, right? And so it's very reliable as well. Internal combustion engines will emit partially reacted hydrocarbons in their exhaust. Has anybody ever heard of rich versus lean burning fuel?
Oh, yeah. No.
Yeah. So that's called rich burning, is when you have too much fuel. And typically engines run a little rich because it makes them more reliable, it causes less damage to the engine, a whole bunch of reasons. And so that's why we need catalytic converters, is because if you don't have that, you'll get soot coming out, it's black smoke, and that's unburned fuel. Okay? That hasn't completely been burned. You've only burned little parts of it. Okay? You'll notice it looks a lot like the charcoal, doesn't it? Ground up charcoal, because it's very similar, actually. Okay? So they will emit those. If you actually run them lean enough, you could actually prevent that from happening, but it gets to a point where it doesn't actually meaningfully do anything for you. Like, you wouldn't actually be able to drive on a highway. You'd put around at like 10 miles per hour. Okay? So the other hydrocarbons, they're not completely oxidized. The carbon soot is what that's called. Everybody good with that? Understands our carbon soot. Okay, so clean burning actually refers to the efficiency of the combustion. So the cleaner a fuel burns, the more complete the combustion is. Okay? Now, distinguishing chemical reactions. These are some different chemical reactions we're going to start talking about, and there are important factors to them. Okay? So for organic reactions, the interesting part is actually how the functional groups change as your reactants form products. Because remember, a lot of the properties of these are from those functional groups, right? So in organic chemical reactions, the structure of organic molecules is written out. The small molecules participating in the reaction are actually going to be shown above this reaction. And so we actually have a slightly different way of showing these reactions when we're talking about organic molecules. And that's because we actually want the three-dimensional structure, or at least the connectivity, to be shown. Okay? Because in a normal reaction, that doesn't matter a lot, right? We're reacting a metal with a gas, okay, salt. And this, that connectivity here, that's kind of all that's changing, right? It's the major thing that's changing. It's very important. And so we want to preserve our space for writing these out. So what we do is we take any small molecules that we don't really care about, and we don't care how they change the structures to, and we write them above the arrow. And so these are other reactants. They're just small molecules that you don't actually have to write out because hydrogen gas doesn't have any interesting structure. Okay? These right here, your reactant and product, are your larger organic molecules that have interesting structure, right? Okay. And you're focusing in on those. This right here is going to be reaction conditions. So below the arrow are reaction conditions. These would be things like a catalyst, platinum catalyst in this case. I have to heat it. It's in an ice bath. Okay? All that sort of stuff. The conditions around it. All right, now, these right here are going to be a biochemical reaction. So when we look at biochemical reactions, it's similar to organic reactions, but we have a slightly different focus. Okay? And that slightly different focus is biochemical reactions are almost always coupled with another reaction. Right? And so, for example, this process right here, this is getting its energy from ATP. ATP is providing that phosphate group. Okay? But we don't really care about ATP that much in this reaction. We could focus on ATP and write it the other way around, but we just don't care that much about ATP in this reaction. We're more concerned about glucose versus this glucose 6-phosphate, okay? And that's what we're focusing on, all right? So see how it's almost the same as the organic, isn't it? We have the thing we're not focusing on. It's the one above the arrow, right? That's a reactant. We put it above the arrow because we just don't care as much about it, okay? And then the one we want to focus in on, this is going to be the glucose here. Our reactant going to our product. And see, we added a phosphate group right there. Okay. Okay. And so this would be another reaction, right? It's coupled to another reaction. And that's what this round arrow means. This is reactant. This is a product. Okay. And it's coupled to that other reaction. This is still conditions. In this case, we have hexokinase. And that's going to be the enzyme for this reaction. That would be the catalyst, right? Okay. Okay. This is the overall chart that kind of breaks these down in case you forget. All right. So this is oxidation reduction. Again, I'm going to call this redox almost every other time from now on. It'd be very unusual for me to go back to the long name. Okay? Everybody comfortable with that? Redox. Does everybody notice how it has both those names in the title? So if you have an oxidation, what do you have to have? A reduction. If you have a reduction, you have to have a oxidation. Okay? They only ever happen together. If you have somebody paying, then you have somebody receiving the payment, don't you? Okay? If you have a killer, then you have to have somebody that was murdered, don't you? Okay? Okay, so definitionally. They typically are going to be two different ways we look at a redox reaction. This way that we're going to start with is actually true for all redox reactions. It's just it can be simplified. We're in organic and biochemical systems. Okay? And you may have heard the biochemical system 1 before if you've taken any biology. Okay? So, when we're talking about inorganic systems where we have metal ions, we're going to usually talk about the movement of electrons, okay? So we're going to have something that loses its electron, and that's going to be the one that's oxidized. So the thing that loses its electron is oxidized. Typically, these are metals. Remember how we have the 1 plus, 2 plus, 3 plus charges? They were getting those charges because they were oxidized and lost their electron. Okay? And so if you lose 1 electron, you get 1 plus charge. If you lose 2 electrons, you get a 2 plus charge, right? Okay. Now, when you gain a negative, when you gain a debt, what do you get? Well, exactly, you get more debt, you get more negative, don't you? Okay? And so, if we gain a negative charge, like an electron, right, we are going to be reduced because it's negative. Okay? And so when you gain an electron, you're going to be reduced. That's a reduction. Everybody okay with that? This is the way I've had the most luck with getting people to understand this, is to go, I'm gaining a negative electron, I'm reduced. And then the other one is oxidation, right? If I lose the electron, I have to be oxidized then. Okay? I'll give you a abbreviation. I have not had much luck with people actually being able to use that to get the right answers. But it's like the most common way chemistry books want people to learn it. You can actually also, if you're good at songs, by the way, go onto YouTube and look up oxidation reduction song. And people have set them to every single tune you can think of. Okay? It's just crazy. All right, so there is an easier way to look at these things, okay? Now, in organic and biochemical reactions, these oxidation reductions are almost always involving oxygen and hydrogens, okay? And so we can actually just keep track of the addition of oxygen or the removal of hydrogen. We don't actually have to keep track of the electrons themselves, right? That makes life a lot easier when you're in organic and biochemical reactions. So let's go ahead and look at an example of this. We have rusting here. So this would be iron solid that has no charge. Okay? That's the metal, right? Okay. Is everybody comfortable with iron metal? Okay. Understands it well. You know, you have steel, that's iron metal as well, with some other stuff in it. And we react with oxygen, we get rust, right? Okay. Okay. So we're going to react with oxygen. Notice these things have a charge of 0 to them. Okay? And so the iron here is going to lose 3 electrons. The oxygens here are going to take those 3 electrons. Right? We know that because the oxygen wants to be 2 minus here. See that? And if we total these charges, that's in 6 minus here, we'd get 6 plus here. And that's 3 on each, right? So that would be an iron 3 plus right there. Okay? So remember, irons, metals typically lose electrons. So the species that's reduced is going to be the one that gained electrons, right? That's going to be the oxygens. The ones that was oxidized was the irons, right? They lost electrons. Interesting side note to this is oxidation's name comes from what oxygen does to things. So oxygen oxidizes stuff, right? It causes oxidation. Okay. Now, the next thing we have to do is, this is one where people have a tendency to get confused, okay? But you just have to remember, this is just how English works, okay? If you have the agent that assassinates someone, were they assassinated? No, they were the assassinating agent, right? So if you have a reducing agent, what did they have to do? They're the ones that reduce the other thing, right? If you have an oxidizing agent, they're the one that oxidized the other thing, right? So the reducing agent is always the one that got oxidized. Okay? The payee is not the one that paid, right? Okay. Okay. You have the payer and the one that got paid, right? Okay. Okay. Everybody clear on that? Okay. Don't forget, agent did the thing to the other. Okay? Okay. So again, if we look at these right here, what we see again is the one that was oxidized. Well, this is the reducing agent, isn't it? And the one that was reduced is the oxidizing agent. Okay? So the oxygen is the oxidizing agent. It does oxidation to the other stuff. Okay, so this right here is actually the acronym that is always put in books and is supposed to be successful, but I have seen very few people actually succeed using it. It's oil rig is the acronym. Acronyms, by the way, 80% of the time do not work. Just as a side note, because people remember the acronym, then they forget what it means, which means it doesn't help at all, right? So anyways, oil rig is going to be oxidation is loss. Oxidation is loss of an electron, right? Rig then is reduction is gain. You are gaining electron. Okay. Okay. Anybody have any questions there? All right. So let's talk a bit about biological systems and their redox reactions. So right here we have a protein. This is called cytochrome C. It's actually an incredibly important protein for ATP production. It's in that last citric acid cycle electron transport chain, in case you're wondering in US biology. Okay? I.e. the mitochondria. Okay? This right here contains an iron 2+. This undergoes oxidation to iron 3+. And then when you lose the electron, it's going to go, when you gain an electron back, whenever you're doing this process, you're going to go back to the iron 2+. And so how it actually works in ATP production is, this is actually how you transport electrons back and forth, and you transport H pluses. Okay? So anyways, the important thing to understand is it goes from a 2+ to a 3+. And so when it goes from a 2+ to a 3+, that is oxidized, right? Okay. The fact that this was oxidized means something else got reduced, right? So this reduces something else, right? And then it can go backwards. Okay. This molecule right here, if you look at this from a three-dimensional perspective, see these little nitrogens right here? They actually point up like a little crown, and they hold that iron in the middle on top. Okay? And so that's actually what these look like. They're called a heme group. Anybody ever heard of a heme before? Like hemoglobin? Yep. And so this is like hemoglobin. Hemoglobin has one of these groups too. All right. So the organic oxidation reduction, this is how you can keep track of them easily in organic and biochemical situations. Notice that if you gain an additional oxygen, bond, that's going to be when you're oxidized. Okay? If you lose a hydrogen, you're going to be oxidized. Notice right here, we've lost a hydrogen on this carbon. See that? No longer has a hydrogen bonded to it. And so that one was oxidized. We gained an oxygen instead of that hydrogen there. See that? That one was oxidized, wasn't it? Okay. If we go the other way to reduction, notice that we lose an oxygen bond here. See that? We gain a hydrogen bond on that carbon. And so that is reduced. That's reduction. Okay. All right, so we fuel our bodies with nutrients that are broken down primarily through oxidation. Okay? The process by which we harvest energy from the nutrients we intake is actually very analogous to combustion. We just don't actually burn things. We do it through a lot more steps, very long pathway in fact, and that's going to be oxidation that pathway does overall. In the body, the process of combustion, again, occurs through this long chemical pathways. It's actually several chemical pathways, depending on the nutrient you're looking at. And this right here is actually going to be called cellular respiration. The respiration portion is where we're drawing in oxygen, right? and then we expel the CO2, which is the fully oxidized carbons. Okay? And that's why it's called cellular respiration, right? Okay. So the ethanol that we saw before, this would actually be oxidized, aldehyde ethanol. This would then be further oxidized in your liver. This can also be called acetaldehyde. The process is actually done by alcohol dehydrogenase. When you do it the next process, so this would be alcohol right here. We oxidize it to this right here. Okay, that's the aldehyde. We oxidize again, we go to the carboxylic acid. And that would be like acetic acid. Okay? And then we actually would urinate that out. All right? Okay, and so that's what happens anytime you go out for a night of drinking. Okay? You will notice that this right here, this aldehyde right there, doesn't exactly sound like something you would normally want to eat, does it? Have you ever heard of somebody eating those, acetaldehyde? No. And it is slightly poisonous to you. Okay? Your body's pretty decent at handling it. And it does oxidize it further down to acetic acid, which also in large concentrations would be poisonous to you. But typically you don't have those large concentrations. And your body handles it pretty well. Okay? But yes, that's part of why you would cause liver damage if you drink too much and too often, is you will slowly start causing liver damage.
This would be alcohol poisoning when like first time drinking, drink way too much.
Yeah, you first time drink, you drink way too much. You've actually backed up your entire reaction to the point where you can't get rid of the alcohol. Yep. Yeah, unfortunately. That's why you can actually, so nowadays they even have pills you can take where it has the enzyme in it, actually. So it has alcohol dehydrogenase in the pill. Yeah. And so it'll actually break down and you'll end up having basically vinegar. Yeah. And so people actually use that trick to like drink tremendous amount at like business parties and get everybody drunk and then get signatures and things.
So do we give that out in the hospital when people come in?
It would be slower than the alternative.
Okay.
The alternative usually is cause them to vomit, right? Because they drank it. Though, interesting enough, that does not help if somebody takes vapor shots or does the tampon alcohol stuff. Did you ever hear about that?
I don't want to hear that. That sounds terrible.
So vapor shots is my day.
Oh, okay.
That was my day in college. That had an LD50 of 1. So you were 50% chance of dying. You took the dang thing. And you couldn't do anything about it because it's vapor. It never hit your stomach. And then the tampon ones, as people were taking tampons and soaking them, then that one was the group of student cohorts that was like 4 or 5 years ago that started doing that. And it still is around, apparently. It's pretty rare now, though. Yeah. I don't know what to tell you guys. I mean, I don't come up with these stupid damn ideas. Sometimes, right? Anyways, when you do oxidations and reductions in your body, there's typically 2 molecules that are going to be involved in those, okay? And the other part of that oxidation reduction is going to be NAD+. So whenever you're doing this ethanol oxidation, that's actually the other side of that that's getting reduced, okay? And then the other one is going to be FAD, okay? And those are the 2 ones that if you ever see those in biochemical systems, typically we're looking at oxidation reduction. We're looking at a redox reaction, okay? Because those are the ones that primarily transport that. This is actually the reaction right here in the biochemical layout. So we're oxidizing the ethanol right here. And then this is going right here to the NADH. And this is the enzyme that does that, liver alcohol dehydrogenase, okay? And that's the product. Notice that is an aldehyde right there. Okay. This right here is going to be a condensation reaction. In a condensation reaction, the easiest way to figure that out and keep track of it, is you'll have water coming off of it. See that? We're condensation reaction because we remove water across it. These reactions are incredibly easy to actually like write out what the product is, because you remove an OH and an H and then you join them onto that bond. Okay? So you literally remove this group right here, remove the hydrogen right there, and then draw the bond over to the oxygen. And there you go. That's it. Okay? Hydrolysis reactions would be the opposite of a condensation reaction. So hydro meaning water, lysis means to break. And so we'll use water to add across that and break it. Okay? And again, it's pretty easy to draw out. You just break one of the bonds, you put OH in the place of it, and then you put the hydrogen on the oxygen there. Okay? And again, hydrolysis and condensation are just the reverses of each other. So, these are extremely common in biochemistry. All these ATP, a lot of these ATP reactions you've seen have been hydrolysis or condensation reactions. That amino acids synthesizing a protein, that was a condensation reaction. Just incredibly common. Okay, all over the place. And so they are the reverses of each other. This one is your hydrolysis right there. We're splitting that phosphate off of ATP. So whenever you're looking in biology, if you ever take that course, or if you've already taken it, hydrolysis and condensation reactions just everywhere. Okay. This right here is the carboxylation reaction. It's going to involve the addition of carboxyl or carboxylic acid to a group. And so carbon dioxide moving from cells is actually typically going to be involved in a carboxylate action. The enzymes that be involved in this are going to be carboxylase and decarboxylase, literally adding carboxyl, right? And then removing carboxyl. And then ACE tells you it's an enzyme. Okay, so this right here is the bicarbonate. Anybody know what bicarbonate is? Like baking soda. You got it. Exactly right. And this is actually reacting with pyruvate, very common biochemical molecule. One of your key like small molecules that's just in everything in your body. Okay. This is the pyruvate carboxylase. See, the carboxylase actually tells you what's happening in the reaction. That's the enzyme. And so we'll have ATP providing the energy for this. It'll link another carboxylic acid on here, and that'll give you the oxaloacetate. Okay. And so that's carboxylation. This one right here is going to be phosphorylation and dephosphorylation. Very common way for your body to take an enzyme and either activate it or deactivate it. Okay? Which way it actually goes, where your phosphorylation versus dephosphorylation, depends on the enzyme. So some enzymes get activated by phosphorylation, some enzymes get deactivated. Depends on the enzyme. Now, notice that they're actually condensation and hydrolysis reactions, respectively. You see how this right here had a water here? And we used it to split these. Okay, so that was a dephosphorylation, but also as a hydrolysis, okay? So both of those are true. And the reverse reaction, in fact, was a condensation reaction and was also a phosphorylation. We added a phosphoryl group, okay? One of these phosphate groups. The enzymes that do these is phosphorylases. That's the condensation one. The hydrolysis one is phosphatases. Okay, so let's talk a bit about hydrolyzable and non-hydrolyzable lipids. Okay, so a hydrolyzable lipid is going to react in a hydrolysis reaction. It'll form simpler compounds, and essentially it's a way to split off the fatty acid here from our normal lipid structure. Okay. Non-hydrolyzable lipids cannot undergo the hydrolysis reaction. Okay. So it's exactly what it says on the tin. The hydrolyzable lipids, these are going to include things like fats, waxes, oils. They're going to contain this ester group. This is the ester group. That's the important functional group that makes them the hydrolyzable lipids that you'll typically see. Whenever you do this reaction, you're going to produce a carboxylic acid and an alcohol. Okay. By the way, when you do this reaction in the presence of metal ions, you can get soap from this carboxylic acid here. Right? That's how you actually make soap.
Lye.
Huh?
With lye.
Exactly. Yep. Yep. So you can use oil and lye and make soap. Okay. That would be a base catalyst. So the fats and oils, these can be hydrolyzed to the component fatty acids and glycerol. And so right here we have a nice oil, and we're hydrolyzing it to form our 3 fatty acids and our glycerol. Okay. The only difference of this reaction versus soap reaction is it's neutral. That's it. Yeah. If you made the salt here, because you're in basic conditions, this would be soap. Yeah. Okay, and so the addition to an alkene, we've already seen this in like hydrogenation, okay? That was an addition to an alkene as well. This is going to be taking a group of atoms. We're then going to add it across a double bond in an organic molecule and break the double bond. And so we take a group of atoms here. This could be H2. That would be the hydrogenation we saw. And we mentioned with like peanut butter, right? Okay. And so this would add across that double bond, and this is going to make 2 single bonds across it. And if this was an alkene and these were hydrogens, that would just be an alkane, right? But we can also do this with things like chlorine gas. We can do it with HCl and add different groups across this. New functional groups. Okay. So hydrogenation and trans fats. So hydrogenation is going to be taking 2 hydrogen atoms. We're going to add it across a double bond. We get an alkane out of it. Now, like all reactions, especially reversible reactions, it does not necessarily go to completion, right? And so if it's a reversible reaction, it can go backwards, can't it? And in hydrogenation, that oftentimes happens, actually. It's pretty easy to happen. Now, it's going to typically use a catalyst. It'll use platinum, nickel, or palladium catalysts. There's a few other catalysts that have been developed recently that I can use, but these would be the most common ones that you'd find on literature when you're looking around. Now, because this is pretty hard to control and it can be a reversible reaction, you can go backwards. And remember how when you go backwards, we could do a cis double bond and we could have a trans double bond, right? So in nature, double bonds are essentially always cis. It is very hard to find trans double bonds in nature. Okay? But when we do hydrogenation of these oils, right, they can go backwards. And in our hydrogenations we do with these catalysts with just hydrogen, when they go backwards, they can be a trans or cis double bond. Okay? And so what ends up happening is if you don't completely react these, you can end up with trans double bonds. And so let's say we did these hydrogenations here. So we did a hydrogenation of this fatty acid here, right? And so the majority of it's probably coming out as the saturated fatty acid. Cool. We have our peanut butter or whatever, okay? Okay. Or fake butter.
Margarine.
Exactly.
Crisco.
I don't respect it enough to call it margarine or Crisco. Fake butter.
Okay.
Butter that doesn't have any real nutritional value. Okay.
Door grease.
Yes. Yes, that's true. Yeah, I hate that stuff. The idea that that was healthy ever just boggles my mind. Aggravates me. Okay. They used to make me eat that junk because they thought it was healthy in the 80s.
Yep.
What the heck? Okay. So when we do this process, yeah, most of them are going to go to the saturated fatty acids. We'll break all our double bonds. We'll go to the alkane, okay? But some of it's going to go backwards. And we're going to have the reversible reaction sometimes. And what that's going to do is sometimes that's going to give us the trans fatty acid, right? That's the double bond in the trans configuration. See that? So we end up with the trans isomer. And these can actually be really damaging to people's health. Okay? They're going to change how your membranes act when you start incorporating them. And you can kind of already see that just from looking at these things, right? We have one cis bond, see how that like curves like this now? And it's not straight anymore? Versus if we have a trans, it stays straight, doesn't it? Okay? So they have very different structure, don't they? Okay. Okay, so this is hydration. This is where we're going to add a water across this double bond. It's typically going to require an acid catalyst. So that's a catalyst right there. And so we're going to add water across it. We put a hydrogen on one end. We put an OH on the other. And this is going to be an easy way we can add an OH there. And we can make alcohols, right? It's kind of cool. Okay. When we have hydration, this position that the OH ends up on is extremely predictable. Okay? And that's because it's always going to end up on the end that has more substituents, that has more carbons on it. Right? So the carbon here that has more carbons, the end of the double bond that has more carbons, is the one that gets the OH. And that's Marconico's rule. Another way of thinking of it is the hydrogen goes on the end with more hydrogens. Okay? And that's Marconico's rule. Okay, that is the chapter. Did anybody have any questions? All right. So we're going to go on to the next chapter. Chapter 6. Dun, dun, dun.